Hi guys, my name is Devesh, and I'm here to share with you a little bit about a natural phenomena that all of us see every day in our lives, but even the best scientists don't fully understand. Gravity has been a sort of a very popular research interest for several centuries, but it became a public interest after the recent movie Interstellar. So let me just start off by showing you a clip from the movie. Here, Matthew McConaughey is stuck inside a black hole, and the only way he can get out of it is by communicating, and he uses gravity to communicate. Specifically, he uses gravitational waves, and he makes this bold statement: gravity can cross the dimensions, including time, which is, well, factually true, but it's a very advanced scientific theory. Before I can get there, let me just take you through a little bit of the story of how we evolved our understanding of the concept. So perhaps the most famous story is Newton and his apple. To give him credit, Newton spent a lot of time building on the theory of gravity until he came up with this famous equation where he found that two masses attract each other by a force that is proportional to the product of their masses and divided by the ratio, the square of the distance between them. A very simple equation, but he used it to model the universe with a surprising amount of accuracy. He could explain how planets orbited the sun and the basic forces of gravity, and it was quite a good theory, but there was one problem. Newtonian gravity was acting at a distance, which meant that if there were two planets several billion kilometers away, and there was something that were to change the force of gravity, that information would travel instantaneously from one planet to the other, which, well, it didn't make sense. Albert Einstein came and found out later that nothing could travel faster than the speed of light. So he felt the need to improve the understanding of gravity and spent 10 years working on the concept with some of the greatest mathematicians and scientists at the time to come up with a set of 10 equations that later became known as the theory of general relativity. General relativity is based on, primarily based on the works of one mathematician in particular, Minkowski, who was working at the time to plot 3D spaces using space curves, very advanced mathematics. And Einstein used this mathematics to formulate a vector equation, a set of vector equations for the entire universe. He called it the space-time continuum. Perhaps an analogy would help. If you picture a trampoline and a bowling ball in the center, the bowling ball is going to warp the trampoline a little bit. And if you put a marble at one of the corners, like the moon here, it will move towards the bowling ball, as though the bowling ball pulls it towards it. That's how Einstein viewed the universe, a gigantic trampoline of sorts with little bowling balls making indents everywhere and little marbles going around and interacting with the universe. And these 10 equations mapped this trampoline, the space-time continuum, and with a surprising amount of accuracy. So here's a little illustration. You can see the little mass in the center, and he's given a velocity to the marbles, and if you notice, they move in elliptical orbits. That's exactly the same orbit in which planets move around the sun, for instance. So it's Einstein himself was surprised about how accurate his theory was. The more, even though they could never disprove it, they never found anything wrong with it so far. But there was one mystery that remained. What if the big mass was to move along the space-time continuum? Let me change the analogy for a second. If the space-time continuum was the swimming pool and the beach ball is the planet, and if you accelerate the planet across the space-time continuum, you're going to expect little ripples to form on the swimming pool. We know that these ripples exist mathematically and theoretically, and we call them gravitational waves. Gravitational waves have never been found, but we know a little bit about them, that they contain answers to some of the universe's greatest unanswered questions. Gravitational waves are information carriers, perhaps the best information carriers in the universe because of some of the properties, and it's very crucial that we find it. And there have been several attempts to do so. I worked at this organization called LIGO, which is the world's largest gravitational wave detector at MIT. Although I don't have enough time to share how it works in specific, the idea is to see what happens if gravitational waves interacts with a ring of particles. So if you picture a ring of particles and a gravitational wave passes through it, it's going to distort the ring in in one of the two ways. But there's already a problem. There are two types of polarizations, and they could come from two different directions and squeeze and stretch them in different ways. So at any point in time, at LIGO, we don't know what we're looking for. So it's a bit hard to detect in the first place. To make it worse, although the stretch and squeeze look sizable, they're actually only by the factor of 1% the size of an atom. The wavelength of a gravitational wave is, analogy, 47 times the diameter of the Earth. And even worse, they move at the speed of light. So it's very hard to detect. And although we have very good equipment, we haven't been able to find it yet. But it's so important that we do find it, because at the very beginning of the universe was electromagnetically impermeable. No light could pass through for the first billionth of a second. So everything we know about the universe comes from after that time. But before that time, the only thing that we know, that we can ever know, comes from gravitational waves. And you can see how Matthew McConaughey communicated using the gravitational waves. These properties, they're small and they're fast. They can move through the space-time continuum without losing much energy. They can move in and out of black holes. They can move, well, yeah, they're probably the best information carriers in the universe, and that's what makes them so important to find. Another thing is that scientists have been obsessed with this idea of unifying quantum theory at the very small level and general relativity at the big picture to form one grand unified theory, or perhaps more melodramatically known as the theory of everything. And gravitational waves remain one of the major missing pieces in that puzzle. Finding these gravitational waves would help us really piece all the pictures together and really understand a lot more about the universe. So it's a very exciting field that lies ahead, and I hope to share with you more at some other time. So thank you so much for listening.
Imran, cue the slide.
Guys, would you like to move